And good morning, everybody. Welcome back to Calc 1. A lot of rushing around this morning. Plan for today, we're going to finish off Standard 14, start talking about Standard 15, have some fun. Usual office hours next couple days. Today at 11 and 1, tomorrow at 10 and 1. I guess other than the fact that tomorrow I have to cut my 10 a.m. office hour a little bit short because we've got a faculty, or no, not faculty meeting, faculty convocation. That's the one. So post a new web work will be due on Monday, and we will plan to have a quiz Friday over Standard 15. Show them. Exams. Matter of fact, I finished grading exams. Something I still need to do is to update everyone's mastery totals on Canvas. I'll do that later today. I just finished inputting everyone's grades into my own personal grade book this morning, so mastery updates will be coming soon. I posted solutions for the exam on Canvas, so if you want to kind of see how I had approached each of these problems, go ahead and I encourage you to check that out on Canvas. I just posted that right before class. Otherwise, be happy to meet with you to talk with you about what you did wrong, what you could do better going forward. Any questions or comments before we get started for today? In that case, a math major once faced the following question on a physics exam. You are given an accurate barometer. How can you use it to determine the height of a skyscraper? So the student answered, go to the top floor, tie a long piece of string to the barometer, lower the barometer until it touches the ground, and then measure the length of the string. Professor was pretty unhappy with that answer. Went up to the student after the exam and said, look, can you give me another method, one that demonstrates your knowledge of physics? Sure. Go to the top floor, drop the barometer to the ground, measure how long it takes to hit the ground. No, that's not quite what I had in mind. Would you like to try again? Okay. Make a pendulum of the barometer, measure its period at the bottom, then measure its period at the top. Try again, Professor demanded. Measure the length of the barometer, mount it vertically on the ground on a sunny day, and measure its shadow. Then compare that to the shadow of the skyscraper? This is ludicrous, said the professor. Again! Walk up the stairs. Use the barometer as a ruler to measure the heights of the walls in the stairwell? Last chance, young man. Find where the janitor lives, knock on his door and say, please, if I give you this barometer, will you tell me the height of the skyscraper? Not always to answer a question like that, it turns out. Some cheekier than others. Okay, so when we left off last class, we had kind of talked about given a graph of a function, how can you determine where a function has a local max versus a local min, an absolute max versus an absolute min, where we said that a local max is a point where your y value is greater than all the y values close by. So for instance, I would say, if we looked at this function, we could say we have a local max at this point right here, as well as at this point right here, at x equals -2 and at x equals 3. And similarly, a local min is just going to be a point where the y value is lower than all the y values close by. An absolute max, on the other hand, was a type of point where the function has its largest y value it will ever reach, no matter what value of x you plug in. So, does this function have an absolute maximum? Aiden?
X minus x equals -2, sorry.
The old minus one. Yeah, at x equals -2. No matter what value of x you plug in, no matter what real number you plug in for x, you're never going to get a larger y value than you would at x equals -2. So at x equals -2, we have both a local max, because it's larger than all the points nearby, as well as an absolute max. At x equals 3, though, we're going to have a local max, because we have larger y values than all the points to the left or right, but not an absolute maximum, because while this y value here is larger than all the y values close by, if we go far enough away, say over here, we can get larger y values, just not close to the original point. Does this function have any absolute minima? Anna? No. This isn't an absolute minimum? Why not?
Because the line continues going on both sides.
Yeah. Good job not falling for my trap of I didn't draw this going down very far. But when we draw this sort of arrow going down, the implication is it goes down forever. Similarly, like that, I would say it keeps going down forever on both sides. So this is going to be a local minimum. It's lower than all the points close by, but not an absolute minimum. Turns out this function doesn't have any absolute minimum. There is no single x value that has the smallest possible y value. Because if you keep going to the left or you keep going to the right forever, you're just going to keep getting more and more negative y values. We also had a sort of a test, the first derivative test, which I'm too lazy to write out again, so I'm going to label it FDT, which says that one way you can tell if a function has a local max or a local minimum at a point is that it's going to have a local maximum at a point if f prime goes from being positive to being negative at that point. So for instance, if we look at this point right here, if we look at a point to the left of this point, f prime turns out to be positive. We're going to get tangent lines with positive slopes. Or another way to think about it is your function is increasing to the left of 3. But to the right of 3, the function is decreasing. We're going to get tangent lines with negative slopes. And so f prime is going to go from being positive to negative, meaning the original function is going from being increasing to decreasing. And according to the first derivative test, that's the sign of a local maximum. If you go from increasing to decreasing. And similarly, if f of x goes from decreasing to increasing, or if f prime of x goes from being negative to being positive, we're going to have a local minimum instead. And we said that there's two types of points where f prime can change sign, going from being positive to negative or negative to positive. And those two types of points are both called critical points, which are points where f prime is 0, where f prime does not exist. So if you're looking for local maxes and mins, these are the two different types of points you need to check. Points where f prime is 0, or f prime does not exist at all. Why? So what I want to focus on today is how can you tell if where a function has local max or a local min without necessarily having a graph of the function to look at. And I think we had started looking at an example last time, but just to kind of come back to it, and this time finish it off, I'm going to look at the function f of x equals x cubed minus 3/2 x squared minus 6x plus 5. And this is going to be a function where we don't have a graph of it in front of us, but we want to tell where is this function increasing, where is it decreasing, where does it have local maxima, where does it have local minima. So, where do you think we should start? We're given this function. We want to determine where is it increasing, where is it decreasing, where is it going to have local max, if anywhere, where is it possibly going to have local minima. What do you all think? James?
Well, there's no x's in the denominator, so we know that there's no point where it'd be undefined for a critical point, but we can find critical points where it's equal to 0.
Where what's equal to 0?
The derivative of this function.
Ah, okay. So James has proposed that we start looking for critical points, it sounds like, which are the points where we could possibly have a local max or a local min. And are also going to be the points where you could potentially be switching from increasing to decreasing or vice versa. So I like that. All right, let's differentiate this bugger. Nathan, what do we get if we differentiate this?
3x squared minus 3x minus x.
Yeah. So we want to check for critical points, which are points where f prime is either 0 or undefined. James, you said you don't think there's going to be any points where f prime does not exist?
Yeah.
Why is that?
Because there's no x's in the denominators, so you can't find a point where it's undefined.
Oh, there's a lot. There's no x's in denominators. There's also nothing else that could cause this to be undefined, like taking square root of a negative number, for instance, or any of the other nasty tricks we've seen where a function can be undefined. This is a polynomial. Polynomials are defined everywhere. You can always plug in whatever number you want for x, and you're always going to get a number as an output. So if you want to find your critical points, I think they're only going to occur if f prime of x is equal to 0. So we need to find the values of x where 3x squared minus 3x minus 6 is going to be equal to 0. So how can we do that? John?
You factor.
Okay. How do we? What do you want to factor?
Factor out of 3 on the bottom of it.
Probably a good place to start. X squared minus x minus 2. Okay, I have factored out of 3.
And then you factor out, and then you factored into x minus 2, x plus 1.
X squared minus 2x plus x will give us minus x. Minus 2 times plus 1 is minus 2. That sounds handy. And if 3 times x minus 2 times x plus 1 is equal to 0, Emma, what values of x are going to make that expression 0?
X equals -1 and x equals 2.
Yeah, we get 2 critical points, because we could have x minus 2 is 0, meaning x is equal to 2, or we could have that x plus 1 is equal to 0, meaning x is equal to -1. So I think we're going to have 2 critical points here, one at x equals -1, and one at x equals 2. So if our function happens to have any local maxes or local mins, it's going to have to occur at those 2 points. We talked about last time, though, just because you have a critical point doesn't necessarily mean you have a local max or min. We could have something like f of x equals x cubed, where we have a critical point at 0, the point where the derivative turns out to be 0, but it's still not a local max or a local min. So how do we check to see our critical points to see if those are the locations of maxes or mins? Well, this one's a little bit sneaky. John, were you going to suggest something?
Well, you can plug answers that are either to the left of -1, between -1 and 2, or to the right of 2, and determine whether the sign becomes positive or negative. And based on that, you can tell whether they're max or mins.
Yeah, so we sort of have a procedure for this. First derivative test tells us that our critical points are the potential locations of local maxes and mins. And to check what we have there, we need to see, is f prime going from positive to negative at one of these points? Or is f prime going from negative to positive at one of these points? And I would say if so, then we have a local max or a local min. But if f prime is, say, going from positive to positive, like it would be doing for x cubed, or if f prime was going from negative to negative, we would not have a local max or min. So what I like to do, I like to draw out a little number line. where we plop our critical points down on the number line. We know at -1, f prime is going to be 0. At x equals 2, f prime is going to be also equal to 0. And what we're going to do is we're going to check points on either side of all of our critical points to see what's f prime doing there. So like, how is f prime behaving to the left of -1? How is f prime behaving between -1 and 2? How is f prime behaving to the right of x equals 2, let's say? So let's do that. Ty, can you give me a point of to the left of -3 to check f prime for?
Left of -3,
Left of -1.
-2.
-3 was the number I had in my head for that, which is why I said that. -2 works well as well. So what is f prime of -2? We don't really care what f prime of -2 is exactly, but what we do care about it is it a positive number or a negative number? Well, it's going to be 3 times, I'm going to use the factored form for f prime here, just because I think that would make our lives a little bit easier. We'll get 3 times -2 minus 2 times -2 plus 1. It's going to be 3 times -4 times -1. Caleb, is that going to be positive or negative?
Positive.
And we're going to have 2 negatives that cancel each other out times a positive. It's going to give us a positive number. It's going to give us 12 specifically, but like I said, I don't care about the actual value. I just care, is it going to be positive or is it going to be negative? And here's a cool fact. Since f prime of -2 is positive, that's actually going to tell us that this function is going to have a positive derivative everywhere to the left of -1. Meaning f prime of -3, going to be positive. F prime of -1.5, going to be positive. F prime of -15 trillion, going to be positive. How do we know that? Well, it comes from the fact that the only points at which a function where f prime can change sign from being positive to negative is at a critical point. Meaning these are the only 2 types of points where f prime can change from being positive to negative or vice versa. So since there aren't any critical points to the left of x equals -1, f prime always has to behave the exact same everywhere to the left of -1. I don't know why I'm doing this with my hands so much this morning. It feels right. I get blood circulating in this hot room. So, since if f prime of 1 point is positive to the left of -1, then f prime of every point to the left of -1 is going to be positive similarly. Any questions or comments related? Lauren. Let's check a point between -1 and 2 for if f prime is positive or negative there. Lauren, can you give me a point between -1 and 2 that we can check the sign of f prime for? 1? Sounds reasonable. If we do f prime of 1, we'll get 3 times 1 minus 2 times 1 plus 1 is going to be 3 times -1 times 2. And Kate, is that going to be positive or negative if we were to multiply that out?
Negative.
We got a positive times a negative times a positive. I think that's going to be negative. -6 to be precise, but again, I don't care about the exact value of f prime of 1. What I care about is that positive or negative? And since there's no critical points between -1 and 2, if f prime of one value of x, like 1, is negative in that interval, then f prime of every value of x between -1 and 2 is going to be negative. Questions, comments, concerns? Emerson, how about a value of x to the right of 2 that we can check?
We can check for 3.
Sounds reasonable. If Emerson wanted to be a jerk, she could have said, oh, Dr. Gerstle, try f prime of 15 pi plus e. Thank you for not doing that.
You're welcome.
If we check f prime of 3, we're going to get 3 times 3 minus 2 times 3 plus 1, which is 3 times 1 times 4. And Franklin, is that going to be positive or negative? Positive times positive times a positive, going to be positive. So what does all of this tell us? Why did we go through this process? Well, the reason why we went through this process is because once finding our critical points and then checking the sign of f prime, whether f prime is positive or negative, between each of our critical points is going to tell us exactly where f prime is going to be positive, 0, or negative when we look at this function. And the reason why we would care about that, is because that's going to allow us to tell where is our function increasing, where is our function decreasing. And also, it's going to help us determine where we have local maxes and local mins. So, where's our function going to be increasing? Not f prime, but our original function. Because I now think we have enough information to be able to tell exactly where f of x is going to be increasing, meaning as we go from left to right, f of x is going upwards. Can anybody give me an interval over which f of x you would expect to be increasing? Okay?
-infinity to -1.
Yeah, we could say from -infinity to -1. Anywhere else? James?
Well, you said increasing in specific.
Increasing specifically.
Okay. 2 to infinity.
Yeah, and over the interval from 2 to infinity. Because f of x is increasing exactly where f prime of x is positive. Because having a positive derivative means you're having a positive slope, so your function's going upwards as you go from left to right. Reagan, where's f of x going to be decreasing?
Between -1 and 2.
Yeah, everywhere else, where it's not increasing, which is going to be over the interval from -1 to 2. So that's how you can determine where your function is increasing or decreasing. You basically just find everywhere where f prime is positive or negative, and if f prime is positive, that means your function's increasing, the original f of x. And if f prime is negative, that means your original function is decreasing. How about local maxes and mins? Are there any points where f of x has a local maximum using kind of the information that we found? Stand out of the way of the recall stuff. Anna?
-1.
At x equals -1? How do you know that?
It is increasing up until that point, and then it decreases after. It's kind of like that.
Yeah. f of x goes from increasing to decreasing at x equals -1, according to our little number line that we found. In other words, f prime goes from positive to negative, and according to the first derivative test, if f prime goes from positive to negative, that's the sign of a local maximum. So we can say f of x has a local max at x equals -1 by the first derivative test, since f prime goes from being positive to negative at that point. Aiden, how about at x equals 2? What's going on there?
That's a local minimum
How do you know?
because it's going from negative to positive.
What is?
The point
Well,
on this the slope.
yeah, the slope, so f prime in other words.
Yeah.
Yeah, exactly. So for similar reasoning, we can see f prime going from negative to positive at x equals 2. So I think we're going to have a local minimum there. So if we go over here, we could say f of x. Is a local minimum at x equals 2 by the first derivative test, since f prime goes from minus being negative to being positive there. And that is how you use the first derivative test to help you find where does your function have a local minimum versus a local maximum. You find your critical points, you kind of determine how is f prime behaving on either side of all of your critical points. I like to use this number line to kind of help illustrate that. You don't necessarily have to, but I find it's a handy tool. And then once you know that, you can determine where is your function increasing and decreasing, where do you have a local max, where do you have a local min. From kind of checking where is f prime positive or negative, where does f prime switch from being positive to negative, or vice versa. Any questions, comments, or concerns? Who can I call on? Nora, I have a question for you. What if, let's say we've gotten +++ here. What type of critical point would we have at x equals -1 in this case? Would it be a local max or a local min? Would it be a local max or a local min? No. What do you mean by no? No, I refuse to answer this question.
It wouldn't, because it's not changing from positive to negative.
It's not a local max because it's not going from positive to negative.
It would be the thing where it goes up and then it swerves to the side.
Yeah, it'd be sort of a point where, like what f of x equals x cubed has at x equals 0. Where f prime goes from being positive to 0 to positive again. And in that case, what would happen is we just have we'd have a critical point that's not a local max or a local min. So in order to have a max or min, f prime has to be changing sign. But if f prime doesn't actually change sign on either side from positive to negative or negative to positive, you just don't have a local extremum. By the way, extremum is a word to mean max or min. Wasn't the case for this function. For this function, both of our critical points were the locations of extrema. One was a max, one was a min. But there are lots of functions out there that can have critical points that are neither of those. Everyone do it okay? I apologize for the state of this room. but such is life. At least it's bright out. Okay, let's do one more. About, we look at the function with a little more spice to it. Let's look at the function h of x equals x squared minus 8 over x plus 3. And yes, James, this time we are going to have an x in the denominator, which is going to cause us some sneakiness. I want to determine where does this function have local maxima, where does it have local minima. So, where do we start? Charlie?
Probably find h prime of x.
Probably find h prime of x. Sounds good to me. Uh-oh, it's a quotient, which means it is time for some low, 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 be high, minus high, be low. I guess that's just one. Really. Low squared down below. We have found h prime. Cool. I found h prime, Charlie. What do I do with it?
So you guys set that equal to 0 to find your critical points.
Ah, find critical points. Okay. Oh boy. Let's simplify this a little bit first, maybe. So if I multiply out our numerator, it's 2x squared plus 6x minus x squared minus 8. Plus 8? Why plus 8?
Because it's minus negative.
Some of you all have a bad habit of doing this. Don't forget to distribute the minus sign. All over x plus 3 quantity squared. I'm not going to multiply that out. Well, if we simplify, we'll get x squared plus 6x plus 8 all over x plus 3 quantity squared. God, crikey, how do I determine where that is 0? I don't know why I said crikey. It's a fun word, I guess.
Could we factor the top part of our function into x plus 2x minus 4, or x plus 4, sorry.
Like that?
Yes.
Ooh, okay. So we get x plus 2 times x plus 4 all over x plus 3 quantity squared. So with that in mind, what are our values of x where we have critical points? In other words, what are the values of x that are going to make h prime of x equal to 0 or be undefined? Emma?
Is it -2, -4, and -3?
Looks like it. If x was -2, that would make this term 0. If x is -4, that would make that term 0 and make the whole fraction 0. If x is -3, that would make the denominator equal to 0, which would make h prime of x undefined. So now we know potential points where we could have local maxima or local minima. At these points where h prime is going to be 0 or non-existent. All right, so now we need to kind of see h prime is going to be 0 here, 0 here, does not exist at -3. Oh my gosh, these are so close together. How do we pick a number between -4 and -3 without going into fractions or decimals? Well, it turns out you can't. Neener, neener, neener. So if you ever get to a problem like this where there's not a nice value of x you can plug in, there's a trick that you can do. Because I'm all for trickiness. Trick is you don't actually have to pick a specific number between, say, -4 and -3. Like we said, we don't care about an exact value of h prime between those numbers. We just need to know, is h prime going to be positive or is it going to be negative? So for instance, if we were to look at h prime of, say, -3.5, since this is our h prime of x formula in factored form, having a factored form for your derivative is really helpful here. If I want to determine whether h prime is going to be positive or negative in there, we could just kind of go through each piece and see, is it going to be negative or is it going to be positive? And then that'll tell us if the overall expression is going to be negative or positive in the end. So, Katie, if we're plugging in -3.5, is x plus 2 going to be positive or negative?
Negative.
So we're going to have a negative expression. How about x plus 4?
Positive.
How about x plus 3?
Negative.
Negative. But it'll be a negative expression squared, which will make it positive. All right, Katie, last question for you. If we have a negative number times a positive number divided by a negative number squared, is that going to come out something positive or negative?
Negative.
I think so, because negative squared is positive, so we'll have negative times positive over positive, which should be negative. Lou, how about if we were to take, say, h prime of -5, give us something to the left of -4. X plus 2, is that going to be positive or negative? X plus 4? X plus 3? Negative squared, so it'll be positive. So if we have a negative times a negative over a negative number squared, positive or negative? This is a case where 4 wrongs make a right, or 4 negative signs combine to make a positive sign, so to speak. All right, let's go. Bleh. Let's do h prime of -2.5 maybe. Morgan, if we're plugging in -2.5, x plus 2, positive or negative?
Negative.
X plus 4,
Positive.
x plus 3,
Sorry. Positive.
so we have a negative times a positive over positive squared,
Negative.
and it's going to come out something negative. And finally, let's check h prime of 0. That's a nice, easy number to check to the right of -2. Who did I call on? I think I may have called on everybody at this point. And I'll come back to you for this one. As h prime of 0, it's going to be, I'll do this, positive times a positive over positive squared. Positive or negative?
Positive.
No negatives to speak of, it's going to be positive. So I'm doing this to avoid having to plug in fractional expressions into things like x plus 2 times x plus 4 over x plus 3 quantity squared. So like I say, we don't care about what h prime is equal to exactly at each of these points. We just need to know, is h prime going to be positive or negative to tell us whether h prime is going to be positive or negative over kind of each interval between our different critical points. So, with that in mind, what's going on at x equals -4? We read off from our table from left to right. Todd?
It's going from positive to negative to positive.
Positive to negative to positive, all at a single point?
It's 0. X equals -4.
Yeah, h prime is 0 there, so we have a critical point.
Yeah.
What's it doing on either side of -4?
It's increasing and then decreasing.
So what type of critical point do we have at x equals -4?
A local max.
Yeah, because we go from increasing to decreasing at x equals -4, so I think we're going to have a local. Get out of here, your last problem. So we can say, since h prime goes from positive to negative at x equals -4, h of x has a local maximum at x equals -4. Aiden, how about at x equals -2? What's going on?
We have a local min,
Why?
because it's decreasing at first, then it starts increasing.
Yeah, so since h prime goes from negative to positive at x equals -2, h of x has a local minimum at x equals -2. How about at x equals -3, Emma? So at this point here, what's h prime doing on either side of -3?
It's decreasing.
Yeah, so it's going from being so h of x is going from being decreasing to decreasing. So what type of critical point do we have at -3?
It's just a critical point.
It's not a max or a min? Yeah, I would say since h prime doesn't change sign on either side of -3, we don't have a local max or a local min there. So it turns out we only have one local max at -4, one local min at -2. All right, James, I have a question.
Well, I had a question for you, but.
I'll let you ask your question.
Okay.
I wonder if it's the same as I was going to ask you.
So at -3, what it look like? So it's like going down and then it goes straight down for a sec, and then it just like evens out going down still.
I'm going to answer your question with my question, and then I'll answer your question. All right, James. Let's say this turned out to be positive at -3. Like, let's say we didn't have the squared term, for instance. What type of critical point would we have at -3 then?
Then it would be a local minimum.
It would be a local minimum? Incorrect. But Dr. Gerstle, that's unfair. H prime's going from negative to positive. Well, that would be true. We would have a local minimum if -3 had been a critical point to begin with. Which it isn't.
Oh, because it's not in the domain.
Yeah! Sorry, that was
Yeah.
that was a sneaky question. But yeah, in this case, I would actually say it's not going from negative to evening out to negative. It's actually going from negative to not existing. If we were to graph this out, we'd actually have a virtual asymptote at x equals -3. It would look something like This function actually looks something like this. Something like that, so to speak. Where at -3, it's going from decreasing to not existing to decreasing. This is at -2. Sure, let's go with that. This is at -4, where we have our local max. But at -3 itself, the original function doesn't even exist. So technically, x equals -3 is not a critical point because h of -3 wasn't even defined to begin with.
So for it to have a local max or min at a point like that, would it need to only be undefined in the
For
derivative?
h prime, but not for h.
Okay.
Yeah. So something like that would be if we had, say, let's say h of x is absolute value of x. Well, we've seen what the derivative of this is. It's 1 if x is greater than 0, -1 if x is less than 0. We found that back in standard 10 using the limit definition of the derivative. So in this case, James, I would say h prime of 0 does not exist, but h of 0 is just absolute value of 0 is just 0. So that would be an example of we can have a critical point where h prime is undefined,
Okay.
and in fact, does not exist. It goes from being negative to positive, so we'd have a local minimum there, which you can kind of just see from looking at a graph of absolute value of x. You have a local min at the origin. But for something like this where your function's not even defined at -3, even if h prime had changed sign at -3, like if we had had something like decreasing to increasing, so to speak, it still would not have been the location of a local minimum because the function's not even defined there.
Okay.
So yeah, I hope that kind of answers your question.
Yeah.
So in order to have a critical point, your original function actually needs to be defined at that point. I will say, however, that it's still good to note where h prime does not exist, say that h prime does not exist at -3. If I were to ask you something about where is this function increasing or decreasing? Because even though you can't have a local max or a local min at a point where your original function is undefined, if I was to ask you where, you can still have that your function changes from increasing to decreasing or vice versa. So if I were to ask you where is h prime positive or negative, where is h of x increasing or decreasing, the fact that at -3 h prime does not exist could affect that answer. Turns out for the specific problem we were looking at, it didn't, but it theoretically could have if I'd given you a slightly different expression to work with. Any questions or comments related to that? All right, that's it for standard 15. But Dr. Gerstle, there's still all the stuff towards the end of the packet relating to extreme value theorem and blah, blah, blah. I decided we're not going to do the stuff towards the end of the packet, mainly because we're a little bit behind where I'd like to be at this point in the semester. So instead of spending an extra class day on stuff towards the end of the packet with extreme value theorem, looking for absolute maxes and mins, I think we're going to move on for now. Come back to it later on if we have time. Morty.
When we write out the answer to where it is decreasing at, does the fact that -3 does not exist, does that need to be reflected in our answer? So you would say -4 to -3, -3 to -2, or would you just say -4 to -2?
I would accept either of those, because that would come down to an individual choice of text. Well, technically at -3 it doesn't exist, so how I would probably say would be from -4 to -3 and from -3 to -2 with open intervals. But if you said from -4 to -2, it could be considered correct in a sort of way in that at -3 it's not changing sign at all. I like -4 to -3 and -3 to -2 a little bit better as an answer. That's how I would write it. but it would not necessarily be wrong to say it's decreasing from -4 to -2. That sort of depends on what your choice of textbook, etc. So there's some extra, so I'll tell you what's on the standard 15 quiz. I'm gonna give you a function like this, no graph, and say, tell me where this function has local maxima, local minima. And maybe ask you about increasing or decreasing. So, general procedure, find your critical points, graph them all out on a number line if you want to use my method. Find where your function is, where your derivative, h prime or f prime, whatever your function is positive or negative. Use the first derivative test to determine whether you have local maxes or mins. And with that, time for standard 16. 4, 5, 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. Hey, does anybody recognize that function on the front page of the packet? It's the one I drew on the board already before class. Surprise. So, standard 16 is going to be pretty similar to standard 15 in that we're still going to be looking for local maxes and mins, but this time we're going to have a different sort of test that we can use. It's not the first derivative test. It's the second derivative test. And what that means is we're going to see how can we determine where our function has maxes or mins instead of relying on using just f prime of x to help us find local maxes and mins. We're going to see if f double prime of x can help us out instead. So, let's take a look-see. Let's take a look-see. Let's find a better piece of chalk. So, what can we say about f double prime of x if we're looking at a graph of the original function? So, in general, we could say that f of x is increasing or decreasing if f prime is positive or negative. If f double prime is positive or negative, we have a different term for that. We're going to say that the original function is either concave up or concave down. So we can say over some interval, let's say x goes from a to b, f of x is going to be concave up if f double prime of x is greater than 0. It's going to be concave down if f double prime of x is less than 0.
What if it equals 0?
Then life is scary. Then you probably have an inflection point, but we'll talk about that in due time. Alright, no, I'm going to answer that question better. Alright, Aiden, let's say you're not feeling up, you're not feeling down. How are you feeling? Give me a word for that.
I don't what really mid. I don't know.
Concave mid, that's the answer to your question. We're going to call it concave mid. If f double prime is neither positive nor negative. No, that is not an actual mathematical term, but you know what? We're going to call it that because you asked the question, you get to name it. So what does that look like graphically? We know what f prime being positive just means you're increasing. F prime being negative means you're decreasing. What on earth does it mean to say that f double prime is positive? So something to keep in mind is that I have students in the class. and my students might have valuable answers, so I should see what they think before giving them my thoughts. So Gabe, I'm gonna go to you.
Well, I was just thinking that if you have, at least if you look at like x squared or minus x squared,
Mhm.
if you take the double derivative of those, you'll either get a positive constant or a negative constant.
Yeah, x squared is gonna have a second derivative of x squared 2x2.
2, which is greater than 0, and it means that it's
Ah, so concave up you think means it looks something like x squared?
it's something like that, yeah.
And negative x squared will have a second derivative of negative 2. So you're saying something that looks like negative x squared will be concave down?
Yeah.
Let's take a look-see. That's actually a great way to think about it. I like that idea, Gabe. What does it mean for a function to be concave up? Well, something to keep in mind is that what does it even mean to take f double prime of x? Like, what is that? By definition, we said f double prime of x is going to be equal to the derivative of f prime of x. That's how you get it. You take f prime of x, and then you differentiate us again. So f prime of x is positive means that f of x is going to be increasing. So what I think concave up means is that f prime of x is increasing. Not positive, but increasing, becoming more and more positive as you go from left to right. So if we look at several different points on the graph of this function, Jonah, what's happening to our derivatives as we move from left to right along this curve? So here it's pretty steep negative, here it's pretty steep positive. What's kind of happening in between?
They're increasing.
Yeah, the derivatives are increasing. It starts out pretty negative slope, but our slope is becoming less and less negative as time goes on, and more positive as time goes on. So our slopes are increasing as we go from left to right. This is fun to do. I feel like I'm in Harry Potter doing wand motions. So in other words, if we have a shape like f of x equals x squared, Gabe, like what you kind of suggested, that means our slope is becoming less negative and more positive as time goes on, and that is going to be the shape of a concave up function. So on the flip side, if you look at a concave down function, what's happening to f prime of x if f of x is concave down? What would f prime of x be doing for a function like this? Anna?
Decreasing?
Yeah, exactly. We could say f prime of x is decreasing. So if we were to take several points on this graph and look at their slopes, as we go from left to right, our slopes are becoming less and less positive and more negative. In other words, our slopes are decreasing as time goes on if we're looking at a concave down function. So a concave up function is going to look something like x squared, Gabe, as you said, where we have increasing slopes from left to right. Concave down function has decreasing slopes from left to right. F prime is decreasing, meaning f double prime has to be negative. Another way you can think about it is, let's say you have two bowls like this. You put them out in the rain. Which one is going to collect water for you? Yeah, the bowl that's upright. If it's raining, this bowl's gonna collect some water for you. It's an upright bowl, it can hold liquids. Upright bowl. Whereas this bowl, you dribble some water on it, it's just gonna come down, go off the sides. It's not gonna hold water for you. That bowl is upside down, i.e. concave down. Might feel a little bit silly, but honestly, that's how I remember what the shape of a concave up or concave down function is. Concave up function looks like an upright bowl. Concave down function is a downright bowl? Is an upside down bowl. So let's take a look at this function. Where is this function going to be, concave up versus concave down? So in general, it's harder to kind of eyeball a function and say, where is the function concave up versus concave down? You could sort of do it, but it's hard to say exactly where it changes from one to the other. Let's look at x equals -2, where we have a local maximum, and an absolute maximum for that matter. Taylor, if we look at the point -2, does that look like a point where our function is going to be concave up or concave down? Yeah, if you drop water on the function, it's not going to stay in this area. It's either going to dribble down and settle down here, or it's going to fall off the side of the function and never be seen again. So I would say, at this point, our function is going to be concave down, has sort of this downward bowl shape. Nolan, how about at x equals 1, our local minimum?
Concave up.
Give me concave up. That's the upright bowl shape. And Nora, how about at x equals 3? Concave down again. What do you know? At our local maxima, the function's concave down. At our local minimum, the function's concave up. That's interesting. Have a good day, everybody. I'll see you all on Friday. So on Friday, we're going to finish off standard 16. It's actually going to be a fairly quick standard. And then I have a fun activity where we are going to be doing a project working for the Coca-Cola Corporation, designing the perfect can of soda. You all have a good one. I'll see you all on Friday.